Hello, y'all. Welcome to lesson 110 of my DP chemistry curriculum. Today we're going over reactivity 3.2.6 and 3.2.7. In 3.2.6, we're going to talk about primary voltaic cells, which are electrochemical cells that converts energy from spontaneous redox reactions into electrical energy. So we're specifically talking about voltaic or galvanic cells. We're going to explain the direction of electron flow from anode to cathode in an external circuit, ion movement across the salt bridge as well. With that, we're going to move on to 3.2.7, where we'll talk about secondary or rechargeable batteries, which involve redox reactions that can be reversed using electrical energy. We'll deduce the reactions of the charging process from the given electrode reactions for discharge and vice versa. Basically, we'll figure out the redox reactions for charging and discharging. We'll also end this unit on a little bit of fuel cells, which is something we covered way back in an earlier section. But with that said, let's jump right into our primary cells or a voltaic cell. So a voltaic cell is what you're going to most commonly see on your DP exam, deriving equations, deriving electron flow and such. But remember, this is where electricity or electrical energy is produced from spontaneous redox reactions. So your spontaneous reaction produces a electrical current. Specifically, we separate the oxidation reaction and the reduction reaction into two half cells connected by a wire. That way, for the reaction to complete, electricity or electrons must flow through the wire and therefore create a current. We have one electrode in an electrolyte. Oops. Per half cell. Just to be clear, your electrodes are going to be your anodes or your cathode. And your electrolyte is just going to be some solution that conducts. Solution that conducts. And it's going to have the metal ion of electrode. So, for example, we can look at an iron half cell. So an iron half cell might look a little like this. You have your piece of iron, your electrode. It is connected by a wire to the other half cell, and it is suspended in a solution. That solution is going to contain iron 2 plus ions, specifically aqueous. So it's going to be able to both conduct electricity, carry a charge, and it has the ions of the metal. We can also represent this half cell. So once again, this is called a half cell because you need two for your primary battery, your voltaic cell. You can represent it as such. Fe, single line, Fe2 plus, and we're going to add our state symbols here. And so what we're representing in this is our electrode, our electrolyte, and this line right here represents our phase boundary, separating the solid electrode from the aqueous electrolyte. So this is what we would use to represent our half cell. You should be able to both write and read this notation right here. So in our half cell, what is actually happening? Well, the metal will form ions by releasing electrons and those electrons would travel through the wire. But because it's releasing electrons, we can say therefore the metal surface is negative compared to solution. The difference in charge between the metal and its solution, difference in charge, is what we refer to as the electrode potential. That electrode potential is quite literally the equilibrium between the metal ions, or the metal and ions in solution. And this is actually found in your data booklet. There is a list of reduction potentials of metals and also other common elements which take place in redox reactions. You can find that, I believe, in section like 17 or 18 of your data booklet. So to create a true voltaic cell, which is also, remember, a primary battery. So to create a true voltaic cell, what you need is your two half cells. So you have two of those half cells together. And those are, once again, connected with wire because you need something to conduct the electrons. And it can pretty much be anything to, you can also have anything as well to harness the electricity. So you can add a voltmeter or anything to harness electricity. So between your half cells, you can add. Now, as soon as you do connect your two half cells, the reaction will immediately proceed and then immediately stop. So as half cells are connected, and we know the reaction is spontaneous, the reaction proceeds, then stops. And the reason it stops is because there is charge buildup at the electrodes. Charge is built up at electrodes. Because if we are forcing electrons through, we are adding a bunch of electrons onto one side, and we are removing electrons from the other, creating an incredibly positive and incredibly negative electrode. So we need something to stop that. So we're going to have a negative buildup at cathode, because remember, red cat reduction happens at the cathode, electrons are coming in, and positive build at anode and aux. So electrons are leaving, creating a positive charge. Now, what we need to solve this is this gets solved with a salt bridge. Now, a salt bridge is one of the most important parts of an electrochemical cell, whether it's voltaic or electrolytic. The salt bridge allows continuous flow, of ions. So this is going to help equalize the buildup of charge. It is a liquid junction of ions, and these are going to be aqueous. So it's going to allow for positive ions to go towards the cathode, helping stabilize that charge. So the positive will balance the negative, and negative ions towards the anode, which will help balance the positive charge. So a couple key details of a salt bridge that you have to know is that one, it separates the solutions of cells. So it keeps the solutions distinct. The electrolytes from the anode and the cathode half cell stay separated. Two, it provides electrical path for ions. And then three, finally, it reduces liquid junction potential, that buildup of charge that we get. So what we need to do to actually visualize this is to just create our own voltaic cell. So what I'm going to do is represent a voltaic cell here. I'm going to start with my half cell, and I'm going to use iron just like I did before. So we have solid iron, and we're going to have a liquid solution, Fe2 plus aqueous. Now, that iron is going to be attached with a wire. In my version of this cell, I'm going to put a voltmeter right there, which is usually represented by a circle with a V in there so I can tell the electrical charge. And then I'm going to create my other cell. In this cell, I might choose something like copper. And so we have our copper electrode, and we have our Cu2 plus ions. Whoops. Just going to scooch this copper over to this side. And those are, of course, aqueous as well. And of course, I'm going to connect with a wire. Now, when I look at iron and copper, from what I learned about ease of oxidation and ease of reduction, I can tell that iron is going to have an easier time oxidizing than copper. It is more reactive. So I can tell that the electrons will leave iron, having a stronger metallic character, a higher ease of oxidation. It's a better reducing agent. Travel through the voltmeter, registering a charge, and into the copper. Because the iron is oxidizing, I know that I'm going to have my anode over here. Because iron oxidizes, therefore I have a cathode on the right side, red cat. The copper is reducing. As this happens, as electrons are leaving the iron will leave the solid state and become aqueous as we are removing electrons. And consequently, the copper, as electrons are being added, will be attracted to the negative charge buildup and form into the lattice of the metallic bond that is the copper electrode. Now, like we mentioned before, this reaction starts and then immediately stops. We get a strong buildup of negative charge as electrons are being added, with a strong buildup of positive as electrons are being removed. Because even though we have ions coming into here, this whole solution, this whole half cell is adding far more electrons. Well, this whole half cell is losing electrons. So this side's becoming positive, this side's becoming negative. The last part we need to add is our salt bridge. So what we are going to do is fill a tube or something with some type of aqueous salt. In this case, we'll use KCl. Now, potassium chloride will split into the potassium and chloride ions. Now, as we said, we have a negative buildup of charge on the cathode. The potassium will leave the salt bridge and enter the solution, while the chloride ions will leave the salt bridge and enter the anode solution. And this is how we keep that flow of charge going, because our charges now won't build up on either half cell. A couple specific things about those salt bridge ions that we want to make clear is that the ions in salt bridge should be inert. We don't want them to react because if they start reacting with the solution, we have a completely different problem that is going to occur. This is not the redox reaction we're predicting. It may be something else entirely. So we possibly don't want a metal ion that is more reactive than copper because we might start getting a problem here. Or sorry, less reactive than copper, because then we might start having a redox here as copper oxidizes to the metal ion. Now, this is our full and completed voltaic diagram, and we're going to learn a notation for that as well. Just as we used this notation right here for half a cell, we can combine two of those notations together. And in this case, we will write it as such. We'll write our anode first, iron, solid. We're going to draw our phase boundary, iron 2 plus aqueous. And now for a salt bridge, we use two vertical lines, and that represents our salt bridge. Then we write our copper 2 plus aqueous, and it just kind of mirrors on the cathode side, copper solid. So this whole thing makes up our entire voltaic cell. Right here on the left, we have our anode. Here on the right, we have our cathode. And right in the middle, we have our salt bridge. And so that is the notation for a primary battery or a voltaic cell. So that's about it for voltaic cells. Let's go ahead and move on to secondary cells or rechargeable batteries. So what makes those different? Secondary cells. So we still use chemical energy, to produce electrical current. But the difference is that as we do this, we can also use electricity or use the electrical current to reset or drive the reaction back to its original state. So instead of this reaction happening forwards and then finishing, we can use electricity to push it back. Now, this still is a very careful process. So you'll notice that almost all rechargeable batteries come with special chargers. And that is because you can kind of blow out your rechargeable battery. So it must be a controlled current to reverse reaction. Now, you'll notice that if you've ever learned a little bit about electric cars, you can charge it or you can supercharge it. However, they suggest you don't supercharge very often because using that much current and power to shove the reversible reaction of your battery back can harm the battery life over time. So that's what we mean when we talk about battery life. It's like how many times it can be reused or recharged. That's how much a secondary cell can be recharged. So you want to be careful about that when you're using current to reverse the reaction. Now, there's a bunch of common rechargeables that you should know about, but there's two main ones. Common rechargeable batteries. Now, the first one is most of your replacements for AA's and AAA batteries. You find these, you can buy them at like IKEA or something. You might see NIMH. What that stands for is nickel metal hydride batteries. So that's one of the most common ones. And then in your phones, your cars, your computers, you have the other most common, Li-ion, which is just lithium ion batteries. So to kind of see how they work, we'll do a simplified example where we'll look at a lithium ion battery. So let's go ahead and explore that one right now. So one of the most common lithium ion batteries is called a lithium cobalt oxide battery, which is LiCoO2. Now, lithium cobalt oxide has a very specific cathode and anode. When we look at the cathode of it, the cathode is just the LiCoO2. The anode, however, is lithium atoms, lithium atoms, and those are absorbed or absorbed into a graphite matrix or graphite lattice. Now, what you may remember about graphite when we were talking about the different forms of carbon is graphite is electrically conductive, and it will actually allow those lithium atoms to move through the lattice. And so that is kind of the main two electrodes we're dealing with. Now, within this, we need an electrolyte as well. The electrolyte is a bit different than any voltaic cell will see. The electrolyte is going to be a non-aqueous solution of lithium ions. So we're going to have our Li plus ions moving around in a non-aqueous solution. So we're not using water for this. Now, we have our two main reactions because we have our reaction at our anode and we have our reaction at our cathode. At our anode, we have our oxidation reaction. So the oxidation. Now we remember that our anode is that lithium in the lattice. That reaction is going to be Li. And for the state symbol, we actually write graphite in because they're absorbed into graphite. So instead of aqueous or solid or whatever, we write graphite. That is going to be converted into Li plus, and that Li plus is in the electrolyte, which we can't say aqueous because, as we stated, it is non-aqueous, plus the electron. So as they're oxidized, the ions move into the electrolyte and the electrons move out. Those electrons specifically are going to flow through an external circuit to the cathode, flow through external circuit to cathode. And you know about this. The external circuit is whatever you're putting the batteries in. So those electrons are going to flow through whatever that battery is powering. Now, once those electrons hit the cathode, we're going to do our reduction reaction. And this is where we get that cobalt oxide reaction. So those Li plus ions within the electrolyte, those are going to gain the electron, and they're going to react with our cobalt oxide. That's a solid. Now, together we finally form our lithium cobalt oxide solid, which is where it gets named lithium cobalt oxide battery. So when we look at this, these are the specifically discharge half equations. These are the discharge half, half cell equations. Discharge meaning it's producing electricity. The difference is when we are charging them, our half cell equations are reversed. So we just reverse the flow of electrons going through it. So to figure out these equations, all you really have to do is just swap it back. And the DP may ask you, what is the charging equation given the reduction reaction of a lithium cobalt battery at the cathode? And to do the charging equation, so why don't we just do an example? The charging cathode equation. Well, given that one above, all we have to do is reverse it. LiCoO2 solid reacts or decomposes to produce cobalt oxide solid plus an electron plus lithium ion in electrolyte. And that is the charging equation at the cathode. So all you have to really know for these secondary cell or rechargeable batteries is how to reverse the equation and state whether or not it's being oxidized or reduced. So when we're charging it, we are producing an electron. We are going from a neutral to positive. We are oxidizing here. So when we are charging, we are doing the opposite of our redox reaction. Now, the last part, I said I would touch on fuel cells, so I'm going to do that very momentarily. Fuel cells. So the difference between fuel cells and those batteries is the electricity is directly generated from redox. And so what we're saying is that the fuel, in most cases like a hydrogen fuel cell, is oxidized at the anode and generates electrons and cations. Now, I said hydrogen fuel cell, so we'll use hydrogen fuel cell as our example. See how they work a little bit. With our hydrogen fuel cells, these usually happen in acidic conditions, and you'll see momentarily why. But you might be able to guess as what denotes a hydrogen by Bronsted-Lowry standards is the movement of a proton. So when we look at our hydrogen fuel cell, the overall reaction is 2H. 2 plus O2 reacts to form 2H2O. I'm excluding state symbols right now, but we can add them in. It's quite simple. The water is a liquid and the diatomic gases are gases. Our oxidation reaction is just simply the hydrogen gas is being oxidized to produce 2H plus, and that's going to be aqueous as water is one of our products, plus 2 electrons. Now, you can note right here, just from the oxidation reaction, we are already producing protons. This will absolutely be an acidic reaction. Now, our reduction equation is 1/2 O2, so we're going to be using half exponents for this, which will also be a gas, plus 2 hydrogen, aqueous, which you can probably guess where those came from, plus 2 electrons, and we make our H2O. And so here we're seeing oxygen get reduced while hydrogen is being oxidized. Now, those electrons are what moves through an external circuit, which is what we use to get electricity for things. That's what powers whatever we're using the hydrogen fuel cell, and the cations will move through the electrolyte. Now, as we finally finish this up, let's look at the 3 different fuel cells compared. I'm going to be taking images straight from Cognitive for this, so give me a moment. So here we go. As we look at primary cells versus secondary cells versus fuel cells, the first thing you want to notice is primary cells are going to be single-use batteries and irreversible. Secondary are reusable and reversible. Fuel cells are continuous. So as long as you continue to provide that oxidant, like your hydrogen for your hydrogen fuel cell, it'll just keep going and going and going and going. You don't really have to worry about charges build up or running out of other aspects of it. Now, for primary cells, they have a long shelf life, they're very cheap to make, and they're very reliable. They'll always work when you need them. Secondary cells can produce you a lot of energy, they can last longer, and they have low environmental impact due to their reusability. But fuel cells have an incredibly high efficiency for how we get the energy out. They have very low emissions and they reduce noise pollution. So when we're using them as opposed to other places where we might use a hydrogen fuel cell versus some other form of energy, like an engine for a car, hydrogen fuel cells are going to be much quieter. Now, the big disadvantages are with primary cells, we have low energy density. There's a lot of waste when discarded. Think about all the single-use batteries that have you've probably gone through in your life, which leads to a high environmental impact. For secondary cells, a lot of our old ones, like lead acid batteries, require maintenance. A lot of things you might see these in are like cars. Most car batteries are lead acid batteries. Nickel cadmium batteries contain toxic cadmium, and that's also harmful to the environment. We don't want it to leach out. And nickel metal hydride batteries have a less durable and shorter lifespan. So even though they're better than the nickel cadmium environmentally wise, they're not as good in the longevity wise. Lithium ion batteries, those are incredibly expensive to produce compared to the others and require careful handling. You've all seen videos of lithium phone batteries blowing up or catching on fire, and that's because lithium is incredibly reactive. Now, hydrogen fuel cells are incredibly expensive to make. The fuel availability is very low. We get a lot of loss in the creation, transport of these fuels. This can lead to environmental impacts as we're talking about how to transport, how to generate and create these fuels that we can use. They're not very durable, and people have safety concerns about them quite frequently. Now, where do we actually use these overall? Primary batteries, where you want that reliability and long shelf life, where you can just pull it off, are often used in medical devices, emergency equipment, and remote sensors. So those will just work when you want them to work, and you probably won't be replacing them often because they're not getting frequent use. They're being used as needed. We use lead acid batteries in cars, like I mentioned before. Nickel cadmiums are in portable electronics and aircraft. Nickel metal hydrides, these are consumer electronics and hybrid vehicles. And lithium ion is literally everything else in your life, including the laptop I'm using and the iPad I'm using, and even the Apple Pen I'm using for my iPad. Now, finally, our fuel cells are being used to power electric vehicles. They're really good as a backup source of power because they have that high energy density and they work as long as you have the fuel, and for generating electricity from renewable sources. So, if you're generating your hydrogen fuel via renewables, it cuts most of the environmental impact of those renewables down because the electricity is stuff you're already getting from a renewable source. The concern is when we start generating power from coal to produce our fuel. So hopefully this helps you learn a little bit more about the different types of batteries, how they relate to redox reactions, and gives you a little bit more insight in how to look at those oxidation and reduction reactions, as well as the anodes and cathodes of our three types of reactions. And have a great night.